various fundamentals of integrated sensing and communication. So today we are very honored to have Professor Weijie Yuan from Southern University of Science and Technology. He will deliver a lecture on Delay-Doppler domain signal processing for ISAC. So before we start, let me briefly introduce Professor Yuan. So Professor Yuan is currently an assistant professor with Southern University of Science and Technology. His research interests include ISAC, OTFS, and low-altitude wireless networks. He was a recipient of Best Editor from the HV CommL, the several Best Paper Awards from HV ICCC, GlobeCom, and also the HV ComSoc and the Information Theory Society Joint Paper Award. He currently serves as an editor for several top-tier HV journals, including TCOM, TWC, TMC, and he is the founding chair of the HV ComSoc Special Interest Group on low-altitude wireless network, and the SIG on OTFS. And he was listed among the world's top 2% scientists by Stanford University and among the as-well highly cited Chinese researchers. Okay, without further ado, let's welcome Professor Yuan's wonderful speech. So, Professor
Yuan. Yeah. Thank you, Professor Liu, for the introduction. I'll show my slides. So you should be able to see it, right?
Yeah, we can see it now. Yeah.
Okay, so thank you so much for attending this talk, and it's my great pleasure to join the series hosted by the SPAWC. So today I would like to introduce some of my research work on the Delay-Doppler domain signal processing framework for ISAC. Okay, so first of all, I would like to introduce something about the Delay-Doppler domain channel. And actually, when we consider the wireless channel, what we usually talk about is how the channel is time selectivity or how the channel is frequency selectivity. So first, let us consider this kind of a static multipath scenario. So we consider that in this scenario, we have two resolvable propagation channels. And the first one has a delay tau 0, which is 2 µs. And there is another path which is reflected by a scattering in the scenario, resulting in a delay of tau 1, which is 3 µs. So for each step, the channel coefficients are given by H0 and H1. So this is how we characterize the channel in the delay domain by using the delay as well as the channel fading. So that is to say, the delay and fading is the basic operation of a wireless channel, and the channel impulse response can be characterized by a single variable function with respect to the delay. Okay, so that is for the static channel case. And now when we change the static case to a dynamic environment, we still assume that there are two propagation paths, but now the scatterings are moving on the road. For example, there are two cars. And here we can see not only there are not only delays tau 0 and tau 1 in the scenario, but also the Doppler frequency, right? The nu 0 and the nu 1. And in this case, which means that we can consider that in a static multipath channel, the basic operation is delay and the channel fading, while in a dynamic scenario, what are the basic channel operations? They are delay, Doppler shift, and fading. So these are the three parameters that contribute to a time-varying multipath channel. So based on these basic channel operations, we want to use the delay Doppler as well as the channel fading to model a channel. So that is the basic concept by using the delay Doppler domain to represent the channel instead of the usually considered time frequency domain. Okay, so here we compare the channel representations in different domains, we can see that. So this figure shows maybe we can refer it to as time delay domain. So we see that first, there are multi-passes in the scenario. We can see there are 1, 2, 3, 4, maybe 5 or 6 passes. And for each pass, we can see the channel coefficients are time varying. So the coefficient will vary with time. So that this figure illustrates how the channel varies along the delay axis and the time axis. However, what we usually see that is the time frequency domain channel, which is obtained by using the Fourier transform, by performing the Fourier transform on the delay axis, and we transform the delay axis to the frequency axis, and we keep the time axis. Okay, so we know that in the time domain, the channel is varying, right? And also, if we consider the frequency domain, if there is a multi-pass in the scenario, so the frequency selectivity will exist, which results in a frequency selected channel. Therefore, if we consider a time varying multipass channel in the time frequency domain, the time and frequency domain will both vary with time, and this results in maybe a very complex channel structure. We can see the interference exists everywhere, and this is known as the inter-carrier interference for OFDM. So based on our previous discussion on the basic channel operations for the delay, for the Doppler shift and the channel fadings, we can actually represent the channel in the delay Doppler domain. So that is what we consider the delay Doppler domain channel. How to obtain it? On the first, on the one hand, we can perform the Fourier transform on the time axis. So here we keep the delay axis and we perform Fourier transformation on the time axis and obtain the Doppler axis. So this is on the first hand side. And on the other hand, we can also obtain the delay Doppler domain channel from the time frequency domain. How to do it? We perform the symplectic Fourier transform. So the symplectic means that we simultaneously perform the Fourier transform on the time axis and the frequency axis. So from the time axis, we convert the time axis to the Doppler axis, and for the Fourier transform for the frequency axis, we perform the inverse Fourier transform and result in the delay axis. Okay, so what happens in the delay Doppler domain? We can see that in the delay Doppler domain, the channel is relatively sparse. There are only some impulses in the channel. And we can also prove this by using the mathematical derivations. So by considering a multipass time varying channel and after performing the Fourier transform from the time domain, we can actually obtain a summation of some delta functions. And the number of summations P is actually the number of scatterings in the scenario. Therefore, for the delay Doppler domain channel model, we can see the delay Doppler domain channel is some delta functions, only P delta functions if we have P scatterings in the scenario. So this is the delay Doppler domain channel. And we can see it more clearly from a three-dimensional view. And this is the time frequency domain channel. We can see the time frequency domain channel is very dense, right? And it is non-stationary. So the responses in the time frequency domain will exist almost everywhere, which means that if we want to accurately acquire the time frequency domain channel, we have to estimate each channel type is, which means for each time frequency grid, we have to estimate the channel coefficient. And it is a bit complex for us to represent it. Moreover, due to that, the non-stationarity of the time frequency domain channel, it will be difficult to equalize. So we have to use a very high complexity equalizer to maybe to mitigate this interference. Okay, so after performing the symplectic Fourier transform from the time frequency domain to the delay Doppler domain, we can see now the delay Doppler domain channel is sparse, and it will allow accurate and low overhead channel estimation. So these are some basic knowledge of the delay Doppler domain channel. Okay, so regarding the main features, I think we have introduced these concepts quite a few times. So the first one is separability, which means that in addition to the delay IDs, we can also use the Doppler feature to separate the propagation paths, even they experience identical delay. And the second one, it is important for us because in the time frequency domain, we usually consider what we call the coherence time. So the coherence time is usually very short because if we consider a moving target, maybe as far as a high-speed train, so the coherence time is very short. But for the delay Doppler domain, we usually consider a stability time, which means that during maybe a relatively short time period, only burst change of the propagation path lengths and moving speeds will cause the channel variations in the delay Doppler domain. So we consider the stationary time instead of the coherence time. And the stationary time is much longer than the coherence time of the time frequency domain channel. Furthermore, as we can see, all channel responses are concentrated. So they are compactly supported by, we can see there is a bound by this solid red line. So why there is a bound? Because in the scenario, the maximum delay and the maximum Doppler can be calculated based on the largest propagation path length as well as the highest moving speed. So moreover, the possible sparsity, which is due to there are only a few significant scatterings in the delay Doppler domain or in the propagation environment. Okay, so these are the main features of the delay Doppler domain channel. And next, let's have a look at how do we modulate the symbols in the delay Doppler domain. So this is the original how to make the system compatible with the existing OFDM system. So first, we have the data symbols placed in the delay Doppler bins. So the delay Doppler modulation is a two-dimensional multiplexing scheme that we have. For example, we have m delay axes and indices and n Doppler indices. Therefore, we have m times n grids in the delay Doppler domain, which means that we can place m times n data symbols in the delay Doppler domain, and we can denote it as XDDLK. Okay, so how to transform the delay Doppler domain symbols to the time frequency domain? So that is the inverse symplectic finite Fourier transform. As we said, how do we transform the channel in the time frequency domain to the delay Doppler domain? We use the symplectic Fourier transform, right? So the symplectic finite Fourier transform, that is a kind of a discrete Fourier transform in a two-dimensional. Okay, so next part is the Heisenberg transform that is similar to our well-known the multi-carrier modulation. So we simply multiplex the data symbols in the time frequency domain onto different subcarriers and using the pulsation and arrive at the time domain signal. Okay, so the receive signal, how to obtain it, that is also very straightforward, which is the convolution of the transmitted signal as well as the channel. But here we consider to use the delay Doppler channel representation for the convolution. We can also use the time domain, it's all the same. So after having this received signal, the RT, we can then convert it to the to time frequency domain symbols, the received symbols. So we can simply use the Wegener transform, or we can also use the classics, the multi-carrier demodulation to transform the continuous time domain signal to the two-dimensional time frequency data symbols in a discrete representation. Okay, so finally, from the time frequency domain to the delay Doppler domain, which is the inverse operation of the transmitter set. So from DD domain to time frequency domain, we use the inverse symplectic finite Fourier transform. And while from time frequency domain to delay Doppler domain, we can use symplectic finite Fourier transform. So finally, we obtain the YDDLK, which is the received signal or received symbols in the delay Doppler domain. So here, what we want to know is what is the input-output relationship between XDD and YDD. Okay, so here we gave this input-output relationship as shown here. So this is a time domain. This is what we have shown. That is a convolution between the channel and the transmitted signal. And in the time frequency domain, so this should be very familiar to all of you, right? So that is the classics, the OFDM, the convolution of the transmitter symbols and time frequency domain channel, right? And also, if you remember that if there are both the inter-symbol interference as well as the inter-carrier interference, so we can easily obtain this kind of equation, the input-output relationship in the time frequency domain channel. And moreover, we can also perform the for symplectic finite Fourier transform on x tilde and y tilde, and we finally obtain the delay Doppler domain input-output relationship. So actually, this equation is a two-dimensional circular convolution of the transmitted data symbols in the delay Doppler domain, as well as the effective channel in the delay Doppler domain. So we can see the summation is still from 0 to n-1, 0 to n-1, but actually because that the effective channel, the HW, is very sparse, therefore we don't have to perform all summation operations. But for this time frequency domain channel, as we see, the HNM, right? You still remember the figure that the HNM has responses almost everywhere in the time frequency domain. Therefore, we have to perform the summations for all n grids along the, maybe that is the time axis, as well as m grids along the frequency axis. But for the delay Doppler domain, we only have to perform the summation for p times, because the effective channel SW has only p non-zero elements. Okay, the input-output relationship in our previous slide can be further written in a matrix form. So for this kind of matrix form input-output relationship, which will be useful when we want to design maybe the detection or to do some the precoding design. So we like this kind of matrix form. So on this slide, we show how to calculate the different edge in time domain, in time frequency domain, as well as in the delay Doppler domain. Okay. So next slide, we show what the waveform will look like in different domains. So we know that in the time frequency domain, the signal looks like the two-dimensional spreading surface, right? So it's like a surface. And also in the time domain, it's like a pulse train. So it consists of different pulses along the delay axis, which is known as the fast time in radar community. And there will be an envelope which is controlled by the phase, and this is also known as slow time. And in the delay Doppler domain, actually it is a two-dimensional localized pulse. So this is similar to what we have shown in our previous slide, that the delay Doppler domain is like a summation of some delta functions. So the basic functions in the delay Doppler domain is a delta-like function. So it's a two-dimensional localized pulse. Even though it is not a perfectly localized pulse, it more like a two-dimensional sync pulse. But we can guarantee the orthogonality between different pulses. Okay, and as we have derived in the previous slide, the input-output relationship between the transmitted delay Doppler domain symbol, the channel, will be a two-dimensional circular convolution. So if we have two passes in the delay Doppler domain channel, so there are two passes, what will happen at the receiver side? So we will perform the convolution of this transmitted symbol, this pulse with this channel pass, and arrive at this received pulse. And again, we perform the convolution of this pulse and this channel pass and arrive at the other one, which means if we transform one pulse in the delay Doppler domain as the transmitted signal, we can actually identify how many passes exist or how many targets exist in the scenario by using this two-dimensional circular convolution. So this property is very useful for radar detection because we can easily find out there are two targets in the scenario. And based on this two-dimensional circular convolution, we can further know by simply subtracting the axis of the received pulse and the transmitted pulse to obtain the delay and Doppler indices of the channel path. So for example, if we place a pulse on the 0, 0 point as the transmitter side, and if the first channel path has a delay index of 2 and a Doppler index of 2, and therefore the received pulse will locate on the 2, 2 grid. And we simply perform the, so 2 minus 0, we have 2, and 2 minus 0, we have 2. So we can simply obtain the delay and Doppler indices related to the channel passes, which can be further converted to the moving speed as well as the range of this target. So by using the delay Doppler waveform, we can very easily to extract the channel information of maybe the geometry information of the environment. Okay, so on this slide, we consider maybe a more complex scenario that we transmit one pulse and one pulse here, one pulse here, and we transmit 3 pulses. So by comparing the delay Doppler domain, the time frequency domain, as well as the time domain, we can see that in the time frequency domain, because we said in the time frequency domain, even we transmit a single pulse, the time frequency domain will be a two-dimensional splitting surface. And if there are multi-passes, for example, 2 passes in the scenario, so the received signal in the time frequency domain will be maybe a superposition of different surfaces. And the resultant figure will be very complex, and it will be difficult for us to infer the transmitted signal and what is the channel. So that is but in the delay Doppler domain, we can see it if we transmit one pulse and we have a 2-pass channel, so we can have 2 received pulses. If we have 3 transmit pulses, we have 2 passive channel. So therefore, we have 6 pulses in the received delay Doppler domain. So these are the benefits. And moreover, we can see that so why we can simply perform the subtraction by performing the received indices minus the transmitted indices. This is because Using the delay-Doppler domain channel perfectly aligns with the basic channel operation. So the channel is contributed by delay and Doppler shifts. And here, by using this kind of delay-Doppler domain channel representation, we can actually reflect how the channel operates on our transmitted signal. So this slide shows waveforms in different domains. Okay, next part, I would like to talk something about the drag transform, which give us another method to transform the time domain channel directly to the delay Doppler domain. So how to do that? If we have a complex time continuous function, which is xt, and we perform the sampling along xt. So and we will choose different starting points. For example, we choose tau1 as the first starting point, and we choose tau2 as the second starting point, and then we perform sampling with the t period. And after obtaining the different samples, we can actually stack it as in a two-dimensional way. So here, this is the samples with tau1, tau1 plus t, tau1 plus 2t, tau1 plus 3t. So here we obtain this. And what's this? This is the tau1, that is the delay axis, which is the fast time, right? And by performing the t period sampling, we again obtain the Doppler information and form the Doppler axis, and this is also known as the slow time. So the Stark transformation allows us to directly convert a one-dimensional time domain signal to a two-dimensional delay Doppler domain signal. So, and again, we can also converting the delay Doppler domain samples to or signal to the time domain by using the inverse Stark transformation. And what are the properties of the Stark transformation? The first one is quasi-periodicity, which means that if we perform, if we consider another t, so here, so here, if we consider perform sampling along the Doppler axis, so what is the period is 1 over t, right? And if we consider to perform the sampling over the Doppler axis, we can see it is actually periodic, which means that the delay Doppler domain signal is periodic in Doppler. And what is the quasi-periodicity? That is because in the in the delay domain. So if we add another period along the delay axis, there will be a phase shift. That is ej2 pi t nu. So there will be a phase shift. And so what are the benefits? This will benefit for communications in the maybe the space air integrated networks. So why? Because that in space air integrated networks, the terminals or the user equipment will moving with different speeds. So usually we have to design different communication protocols for this kind of communication devices. But by considering this periodicity in the Doppler domain, even the moving user equipments are with different speeds, we can actually convert them in a fundamental rectangle. We will take so in this area. So we always have a fundamental rectangle in the delay Doppler domain with a range tau in 0 to t and nu in 0 to 1 over t. So regardless how large the speed is, we can use this periodicity to transform the delay Doppler domain signal into this fundamental rectangle by using these shift properties. Okay, so we have introduced some basic knowledge regarding the delay Doppler domain framework as well as the signal processing. So next, I would like to introduce the delay-Doppler domain-based ISAC. So why we want to consider the delay-Doppler domain for ISAC, because that there have been a lot of works on the OFDM for radar sensing. So let's have a look at the classic sensing problem. What we want to obtain is the locations and the speeds of the targets, right? So to obtain the target location, we usually rely on the distance-based scheme. So we have at least 3 anchors or reference nodes, and we should obtain the range between the anchor of the reference node to the target. So with the anchors be the centers and the corresponding range distances be the radius, we can illustrate 3 circles, and the circles will have an intersection if the measurements are noiseless. But if there are some noise, we can obtain a decision area. So there will be a region, and we can perform some estimators to determine the target location. And here we show that what has Doppler shift. So if we want to know the speed, the most direct way is to use the Doppler radar to calculate the Doppler shift of the target. And by using a very straightforward manipulation, we can convert the Doppler to the moving speed. So here from this figure, we can conclude that if we want to obtain the target location or want to know the speed of the target, we actually want to know what happens in the delay-Doppler domain. So therefore, if we consider to use delay-Doppler domain for both communications and sensing, so we actually have a kind of a unified domain, right? So by using this kind of a unified domain for communication and sensing, we actually unify both functionalities in the same domain. And as we discussed, the delay-Doppler domain represents the basic channel operations. So we can convert the nonlinear channel operations to linear one, because we see that in the 2-dimensional circular convolution, what happens in the delay-Doppler domain is the movement of the grid, right? And also the channel fading will place a maybe a multiplication onto the original transmitted symbol. And moreover, perhaps if we can use a unified domain for both functionalities, perhaps we could have more degrees of freedom for signaling design. So that's also some basic knowledge. Okay, next I would like to introduce some of my works in this area. So the first one that is to use the sensing to assisted communication in the delay-Doppler domain. So this is also based on what we have done maybe in last few years, the predict beamforming. So we consider there is a roadside unit, and it will transmit ISAC signal to these vehicles. So on the one hand, the vehicles could decode the information contained in this ISAC signal, and on the other hand, the ISAC signal will be reflected by these vehicles and can acquire the echoes. So the roadside unit can further use this radar echoes for inferring the states, the locations, and the speed of these vehicles. So let's have a look at the system model. We again consider the delay-Doppler domain modulation. So that is a delay-Doppler domain modulation, and we convert it to the time frequency domain, and finally to the time domain. And again, we consider to use the beamforming scheme by simply steer different beams to different vehicles by using this A theta I. And for the sensing channel, so the sensing channel what is sensing channel? Sensing channel is the transmitted ISAC signal, the downlink signal, and the reflected, and we acquired, and this is what we call the sensing channel. So it is given in this equation. And on the other hand, what is the received communication channel? So the communication channel, we can see it has a very similar form as the sensing channel. So what the only difference is that for oh, sorry, that is the sensing channel and the sensing receive signal. So for the sensing receive signal, it will has the gamma I and omega I. So both gamma I and omega I are the round trip delay and the round trip Doppler frequency, right? Because we send the signal from the roadside unit and it is reflected by the vehicle. So there is a round trip. Okay, if we take a look at the communication channel, so what we can observe, that is here. So we didn't show it here. So for the downlink model, if we consider that there is maybe a large area as a roadside unit, so we can almost the has a line of sight dominated channel. So this is a line of sight dominated channel. So this is the transmitted symbol and here is the beamforming gain. And for the uplink channel, if we consider the vehicles only have one antenna, so the uplink channel will be a multipath one. So it's given here as shown here. So it's a two-dimensional circular convolution between the transmitted symbol as well as the uplink channel. So here, the most important equation is here. So this is what we know as sensing receive signal. So from the roadside unit reflected by the targets and received as the roadside unit again. So in the sensing received signal, we have the round trip delay and the round trip Doppler, right? And for the uplink channel, for the communication uplink channel, what we have the one-way delay and one-way Doppler, because we consider to transmit the from vehicle to the roadside unit, right? So it's a one-way delay and one-way Doppler. So this means that we can using the sensing parameters to predict the communication channel. So in some previous predictive beamforming frameworks, we usually consider to use the sensing parameters to predict the angle parameters, and then we can predictively steer the beamforming vector to some intended direction. But here, by using this kind of a delay-Doppler domain channel, we can even predict the communication channel, because that, as we discussed, the delay-Doppler domain channel is slow time varying. So this kind of framework has three steps. The first one, that is to estimate the state, which we use the reflect echoes for estimating the motion parameters, for example, the delay Dopplers and the angle parameters. And then we can use this delay Doppler and angle parameters to reconstruct the dynamic topology of the whole vehicular networks. We can infer the locations and the speeds, and then we can predict the topology in the future time if we have already obtained the locations and speeds of all vehicles. And then we can use the topology information to reconstruct the delay Doppler domain channel to assist communications. That is how we use the sensing parameters to assist the communications in the delay Doppler domain. Okay, so this figure compares a frame structure of different schemes. So by using this kind of sensing assisted communications, we can maybe bypass the transmission of pilot and the feedback procedure, which will help us to save the spatial resources as well as to enhance the efficiency. Okay. So what we can do now, and let's see, if we have already obtained the sensing parameters, and then we construct the dynamic topology of the vehicular networks, and then we can use the roadside unit to predict the channel path loss and the Doppler shift for the downlink channel, because we see for the downlink channel, we consider that it is line of sight dominated, right? So how to do that? The HI bar, which is the predicted channel parameters, this can be obtained by using the predicted location of the ICE vehicle, and we can simply obtain this. And if we have the location of the ICE vehicle and also for the predict speed of the ICE vehicle, we can further predict the Doppler shift related to the ICE vehicle. So if we have HI bar and nu bar, we can perform the pre-equalization at the transmitter side, which means that as the vehicle side, a single type detector can be adopted without performing equalization at the vehicle side. So this would greatly help to reduce the receiver complexity as well as the latency at the vehicle side. Okay, then let us consider about the uplink case. So for the uplink case, what we have the topology of the vehicular networks, which means that we have the locations, we have the speed. So we have the delay and the Doppler shifts of different channel passes of the uplink channel. So although the channel gains are random variables, so even if we know the delay indices and Doppler indices of the channel responses, but we still don't know the channel gains because they are modeled as random variables. But what we know the interference pattern. We know if we place a pilot here, where will it go, right? Based on the two-dimensional convolutional circular convolution property, we know where the pilot will exist after transmitting the channel. But now, so this is for some classic delay Doppler domain channel estimation scheme. We will place the guard space to avoid the data interference between data symbols as well as the pilot. But now, if we already have the knowledge of the interference pattern, we can get rid of the guard space and further improve the spectral efficiency. Actually, we have considered a case without guard space. So we place data symbols in the delay Doppler domain and occupy the whole delay Doppler domain. And here we place a kind of a superimposed pilot data scheme. So we place a pilot here. And because that we already know the interference pattern, we already know what will happen. We already know the channel operation to this pilot symbol. We know the channel will move this pilot to what location. So this will help us to actually maybe at the receiver side, we can simply see what happens on the grid that the pilot will move to. So based on this no interference pattern, we can cancel the interference induced by data symbols after detection. And then we can refine the channel estimation. And again, the refined channel estimates can be used for improving the detection performance. Okay, so here we provided some numerical results, and we can see that. So first of all, our proposed algorithm can almost approach the perfect Gini-aided scheme. And compared to the conventional, the feedback-based scheme, because that our proposed the approach can use the whole downlink block as a pilot. Therefore, it can achieve a higher signal-to-noise ratio gain. And moreover, as shown on the right figure, we can see that. So the channel prediction of the delayed Doppler channel is sufficiently accurate. So this line is the ideal case with perfect channel state information, and here is the brown line that is we use the predict channel for the downlink detection. So we can see that the predicted delayed Doppler channel is sufficiently accurate for downlink transmission. So we don't need to perform transmission. We can predict the channel and perform the pre-equalize at the transmitter side. So for this brown line, we don't need to perform equalization at the receiver side. We simply perform the data detection. So that is our first work on the sensing assisted communication in the delayed Doppler domain. So in next, let me introduce another work on using the delayed Doppler waveform for radar detection. So first of all, the delayed Doppler received signal can be expressed by this equation, right? This is a two-dimensional circular convolution, and here we consider to aid the phase shift to consider the use of the practical rectangular pulse. And if we only place a single pilot, as we said, if we place a single pilot and leave all the delayed Doppler domain as a gas space, the received delayed Doppler signal has the shape of this figure, and we can see the target responses and associated delays and Dopplers can be easily obtained. We can very easily see that there are 4 targets in the scenario, and we can easily extract the delay and Doppler information of these 4 targets, right? So this is very good for radar sensing, and but this does not meet the requirement for information transmission. So if we consider this case, we only transmit one data symbol in the delayed Doppler domain, and the spectral efficiency is very low. However, if we use a whole frame to transmit data symbols, what will happen? We can see the received delayed Doppler domain signal becomes more complex. And this is due to that all data symbols will transmit through the delayed Doppler domain channel, and the interference will greatly affect the target response. Okay, so how to tackle this issue? We consider a very simple two-dimensional correlation scheme. So here, that is the VDD. So the YDD, which is the two-dimensional circular convolution of the delayed Doppler domain channel and the transmitted signal. So here we further perform a two-dimensional correlation of the received signal and the transmit signal. So it's kind of maybe you can regard it as mass filtering in the delayed Doppler domain. And what will happen? It will have the effect of the two-dimensional pulse compression. We can see that. So after two-dimensional correlation, so this is what we received for YDD. And after two-dimensional correlation, we can see we can again extract the 4 targets in the scenario. So there are 4 targets in the scenario. And actually, by using this two-dimensional correlation, we have revealed intrinsic connection between the range Doppler matrix computation in radar sensing as well as the delayed Doppler demodulation. So this is how do we calculate the range Doppler matrix, and in the same time we have done the demodulation. And here, let's have a look at the sensing performance based on the delayed Doppler waveform. So for both the velocity and the range estimation, we can see by using this kind of two-dimensional correlation scheme, it has a better performance than the OFDM signal. So, however, due to the overlapped the responses caused by communication data symbols, we can say even we further increase the signal to noise ratio, we cannot increase the sensing performance. So actually, this is our initial trial on this topic. And we understand that we can see that the two-dimensional correlation is very simple, but it will has a relatively high complexity. So perhaps we could to do more things to achieve a good trade-off between the sensing and the communication performance. Okay, so this is one of our other works on the optimal signal design in the delay-Doppler domain. So if we want to perform the radar sensing, what we want to do is to obtain the optimal ambiguity function like this, right? So we hope that the ambiguity function will have only one response at the 0, 0 grid, and all the other grids will have responses of 0. So that is the ambiguity function, and this is a discrete form of the ambiguity function. So the wheel sequence is a well-known sequence designed for radar sensing, and we can see this kind of ambiguity function for the wheel sequence will has a spike at 0, 0, the origin point, the origin, and all other grids will have a relatively low side lobe. So this is a good ambiguity function for radar sensing. Okay, so now if we want to know the optimal radar signal in the delay-Doppler domain, what should we do? Again, we will minimize the integrated side lobe, the ISL, in the delay-Doppler domain. So this is what we do. So first, we write how the integrated side lobe express like this. So this is the transmitted signal, this is transmit signal, and this is the Hermitian of the transmit signal. And here the JK and DL denotes the channel basic operation along the delay axis and along the Doppler axis. And so the S can be further converted to the Fn, the coordinator of Fn, Hn, Im times X. So X, this is the delay Doppler domain signal. And here we convert it to the time domain signal. So to calculate the ambiguity function. So after some calculations, the minimization of the ISL, so this equation is very complex, but after some manipulations, we can actually reduce the integrated side lobe here as a very simple equation. So what we want to do is minimize this integrated side lobe. Okay, so we formulate this problem as here, and we have two constraints. The first one is that we have a matrix X, which is a column vector X times a row vector XH. And also, we know that the trace of the matrix X will only be n, which means that because even though the X might be so this is because that we only have n independent data symbols, the X here. So this optimization problem is very difficult to be solved. So we perform a relaxation. So we relax the X equals XXH, this constraint. And here we formulate the optimization P2. And by solving the optimization problem P2, and by considering that the X is a column vector, we actually obtain the optimal X. So what is optimal X? That is to say, we place a single pulse in the delay Doppler domain. which means that if we want to design an optimal sequence in the delay Doppler domain, we can simply put 1 and all other grids are 0. So 1, 0, 0, 0, that is the optimal sequence in the delay Doppler domain from the radar sensing perspective, from the minimization of the integrated side lobe perspective. So we can place a 1 on any grid in the delay Doppler domain while set all other grids to 0, and this will give us the optimal delay Doppler domain sensing signal. So that is another topic. And as we discussed in our previous conference work, we have discussed that we want to strike a trade-off to obtain good communication performance while to obtain a good sensing performance. So now suppose we've already have a good sensing sequence with good radar properties, which is defined as S radar. And here we have a question. So how do we design a precoder so that we can have a good signal that serve both sensing and communication well? That is what we do for this part. So here we consider the transmitted signal is given by S. So the S is a communication signal, a communication sequence. It has some random information symbols. So we can convert it to the time domain. So by using this DFT, the discrete Fourier transform along the Doppler bins, and we keep the delay bins. Okay, so here what we want to design is the precoding matrix W. So the W is the delay Doppler domain precoder to be designed. And what we do is we have the sequence and we perform precoding, and then we convert it to the time domain and for the antenna mapping. Okay, so for okay, so for sensing, what we care is about the side lobe, the integrated side lobe, right? So we again calculate the side lobe here. So the UKL, which is the combination of the JK and the DL, that is can be seen as a hypothesized sales KL, and it's kind of operator to perform on the sensing reference signal S radar. So here to simplify, we can denote the bracketed term by Q. And actually, the Q can be regarding as a Hermitian, the PSD weighting matrix that encodes the SIN dictionary KL and the reference signal S radar. So the S radar is what we say we have a a sequence with good sensing performance. Okay, then we take in the expectation over the random data S, or also it can be seen as performing the expectation over X. And finally, we obtain this equation, which is the trace of the precoding matrix, the Hermitian of the precoding matrix, and the weighting matrix Q. Okay, with that, so what we want to do, we said we have already got a good radar sensing signal, and we want to what we want to is to design a precoding matrix that has good radar sensing performance as well as has a good communication performance. So here we formulate the problem as here. So here what we do is to maximize the normalized log determine the data rate. So given this equation, and here the trace the W2 dot Q, the trace of W2 dot Q is actually this equation, right? This we have defined it as integrated side lobe, right? So we can set CC0. So the CC0 is what we set for the integrated side lobe. We can set a smaller C0 to achieve a low side lobe level, and we can maybe set a higher C to maybe to relax the requirement for radar sensing. And here we suppress the side lobes over the omega. So this is the region of the omega. And figure A shows the magnitude of the optimized the precoder W. And we can see the energy concentrated along only a few dominated delay-Doppler nodes, and with many entries effectively driven towards zero because we want to suppress the integrated side lobe. So figure B shows the magnitude of the precoded symbol matrix Wx over the delay Doppler domain. And we can see the region omega is the indices in the region omega are almost zero, which means that we steer the power into other grids while we put almost non-zero in the region omega to guarantee the sensing performance. And we will steer power, we will allocate power to other grids to help the communication rate. So based on these two figures, we can have some observations. So first, if we want to have a very low integrated side lobe level, and the solution is to force the omega to nu. So here this is nu. So to keep this the energy in this bins very low and to steer powers into other permitted bins to help the communication rate. And and moreover, a very important thing is that we can see the rank of the W2 is approximately the mn minus the cardinality of the omega. So which means that if we want to transmit more data symbols, we can relax the C0 and we can have a higher rank of the W2, and so we can make sure that the region is not as large as what we expect. So by using this way, this actually reflects the original delay Doppler domain channel estimation. In the original delay Doppler domain channel estimation, we need to place the gut space to avoid the interference between the data symbols and the parallel symbols, right? And here we have shown that through the optimization based algorithms, we actually arrive at a similar conclusion. So if we want to guarantee the sensing performance, then we need the gut space. We need to make sure that the energy in these bins are almost zero and to allocate the energies to the power to other bins. And if we want to maybe to increase the data rate, then we can relax the requirement for the sensing the integrated side lobe level. So this gives us some possible trade-offs between communication and sensing by properly design the pre-coding matrix. Okay, another topic that is to use the communication estimation, the communication channel estimation to assist in radar sensing. So what we consider here, which is because that, as we discussed, the delayed Doppler communication channel has actually reflected the propagation environment. So because that the delay corresponds to the range and the Doppler corresponds to the speed, right? So therefore, if we can obtain the delay Doppler domain channel estimation, we can then extract the delay and Doppler information, and then we can know the position and the velocity of a moving target sensor. So here we consider this kind of bistatic sensing scheme aided by communications. So we consider there is a moving transmitter, and the moving transmitter will transmit a signal, and the signal is reflected by the target and received by some distributed receivers. So based on the delay Doppler channel estimation, we can actually obtain the delay of this path, right? And Doppler of this path, as well as the delay and Doppler of the path two. So based on the different passes, our aim is to estimate the three unknowns: the transmitter location, the target location, as well as the target speed. So in a bistatic path, we are the receiver L, and we have the measured range is from the path, the transmitter to the target to the receiver. And we can minus the baseline. So from the transmitter to the receiver, we have a line of sight path, and we can minus this path. And so that is what we do. That is a range. And also we have a range rate, which can be seen as the first order derivative of the range parameter. So after some manipulations, we can actually formulate this kind of optimization method. So actually, this is very hard to solve directly because of those bilinear terms. So there are several bilinear terms. So therefore, we consider to use a very simple semi-definite relaxing algorithm to convert the non-convex problem to a convex problem. And then we can solve this problem very easily. Okay, so here we have tested the robustness under correlated measurement noise. And we can see for our proposed algorithm, the dynamic SDP, we can see we can perform better than the two algorithms in the literature, right? And also the middle plot, this figure compares the recovered target trajectories under correlated noise. And we can see that our proposed algorithms can accurately can perform better than the joint SDP for tracking the trajectory of the target. And so this figure shows that the estimation results, the MSE for both position and velocity, and we can see with the increase of the SNR, we can observe monotonically decreased the performance. So that is for the communication system. Okay, so in our previous work, we consider that there's only one target, and we don't have to distinguish at the receiver side the signal is from which target. But this will be a very important one if we consider there are multiple target sensing, right? So for example, if here we have three targets in the scenarios, and for each receiver will receive. So if we have two transmitter, so each receiver will receive 6 different measurements. So we have 6 different pairs of tau I and nu I. And for receiver 2, we also have 6 pairs. So now what we want to do is to perform the pairing. So we want to know if we have a pair of tau I and nu I, whether the tau I and nu I belongs to the car, belongs to the track, or belongs to the bus. Therefore, we have to solve the data association problem. That is the measurement to target association problem. So because that, the receivers lacks awareness of the associations between the extracted measurements and the individual targets. So what we do here is to actually, because we have different transmitter, different receiver, and different target K. So for each pairs of each group of receiver J, target I, a transmitter I, and target K, it can produce a range and range rate measurement. So our goal is jointly associate and localize by minimize this kind of total squared association error or permutation error. So these are the permutation error. So here the G is a binary 1-to-1 constraint. So it can be 0 or 1 to associate the measurement to a target. Okay, so this also is very difficult for solve because if we want to solve this problem directly, it's very difficult because we have several norm terms and also there is a unit vector inner product makes the convex, non-convex, and also the binary G will further complicate the problem. So what we do here is to use the successive convex optimization, which is to introduce the first order Taylor expansion of the Hij on the PUK and PUK dot. So with these linearizations, each equality will involving norms or unit vector projections will becomes a fun in the P and the P dot. So now the problem can be solved by using some convex optimization schemes. Okay, regarding the result, and we can see on the left figure we compare the data association errors versus the measurement spread, and we compare our proposed algorithm with the neighboring, so the best range based the data association. So we always find the association pair that has the lowest range error. So our method can roughly half the incorrect association, and we can see the gap will increases as the sim becomes noisier. So which means that our proposed algorithm will perform better when the noise is more significant. And here in the middle, we can see that. So for our proposed algorithm, it can almost attain the Cramer lower bound, and it will drop steadily with SNR. So, which means we can almost track the correct association. And for the roof estimation, because we don't consider the data association, so the performance is very bad. And also the result can be seen also for the velocity estimation. Okay, so for the final part, we would like to introduce some implementation results based on the USRP. So here, this is what we do in our laboratory. We have used two USRPs, one as a transmitter and one as a receiver. So here, this is the data and pilot placement. So we place data symbols in this part, and we place a pilot, and also we place some guard space surrounding the pilot. And then here, so after transmitting through a channel, we can see first the data symbols are interfered by the channel. We have to perform equalization. Moreover, we can see for the pilot that it will be moved to this point. This is because that there will be some moving target in the scenario and will result in the movement of our pilot location, the grid. So by subtracting the delay indices, the index and Doppler index of the blue point and the yellow point, we can actually calculate the speed and also the range of the scatterings in this scenario. So this is what we do. And so here we consider to perform some experiments for what we talk the communication assisted sensing. So here we consider we have a transmitter and we have a receiver, and there will be maybe a robot car in this scenario, and then we can extract some information. But however, so after some experiments, we found that the speed of the robot is not high enough to generate a significant Doppler shift, because in the scenario, maybe the robot can only move at 5 meters per second, so it's very slow to produce some significant result. So therefore, here we consider to use the equivalent channel. So what we do is to manually add some targets in the scenario. So to generate a emulated channel. And here we have a real channel. Real channel is a multipath channel in this kind of laboratory. And so the equivalent channel is a convolution of the emulated channel and the real channel. So actually, from the results, we can accurately obtain the location and the speeds of the targets in this illuminated channel. So to prove the effectiveness of the proposed schemes. And moreover, we have used the SDR devices to perform the hand and the body motion. So again, we will have a transmitter antenna and a receiver antenna, and we will perform different hand motion and body motion to maybe to obtain some data, and then we will train using this data to train a model for the motion identification. So we can see that for the hand motion, we can see by using the delay Doppler domain, we can more clearly see what the hand motion will affect the channel. We can see here that is the kind of the back and forward movement. So if we perform the hand and forward motion, we can see a burst of alternating positive and negative Doppler, right? So the hand moving and toward and away, so we can see a significant alternating the positive and negative Doppler. But if we only consider the forward motion, so we consider forward motion and move the hand away, we can see the most Doppler are positive, right? Because we only move forward. And if we consider only the bike, so we just put our hand here and move it back, and we can see it will only generate some negative, the this kind of a negative Doppler. And here we have tried another back and forward motion with faster move and forward and back motion, and we can see it will produce maybe a stronger channel responses in the delay Doppler domain. It has a higher frequency of the alternating between the positive Doppler and the negative Doppler. And for body motion, we can also see some results, but because that for the body motion, the Doppler the Doppler effect is not that significant, so we can only maybe observe this kind of the body forward and backward. We also have a positive and negative Doppler, and because that the moving speed of the body motion is not that high compared to the hand motion, so we can see the change frequency is also not that high. So that is for some initial results. So actually, this is what we what we design for this system. So we perform the body motion and hand motion. So we perform the human recognition, and at the same time, we also consider to fulfill the communication functionality, to perform the transmission, to perform equalization, and finally we want to recover the constellation. So after transmitting through the channel, we can see the constellations are maybe very messy, right? So we have to perform the equalization, and then we can separate these constellations. And at the same time, we want to use the waveform to recognize what kind of the human recognition. So what we say, the hand motion. Okay, so here we have done some experiments. We have compared, we have stored the data sets for different motions, such as the slide, the roll, the clap, the sweep, the push-pull, and circle. So first of all, from this kind of motions, we can clearly, or we can directly observe what happens in the delayed Doppler domain channel. So this is a benefit compared to the time frames domain. So in the time frames domain, we have to perform some signal processing and to see what channel happens. But in the delayed Doppler domain, we can see that there will be a positive Doppler, negative Doppler like this, right? So we have different patterns for the delayed Doppler domain channel to represent the different motions, the hand motions. So finally, we have compared different environments. So we have we trained the learning model by using the dataset obtained in the office. And actually, we classify 6 gestures: the sweep, push, roll, clap, circle, and slide. So we train a very lightweight CNN, a convolutional neural network, to identify the different human gestures. So for the first figure, we train and test on S1. So we train here and we also test here. And we can see the confusion matrix yields 95.5% accuracy, and the diagonal dominance is very strong. So the accuracy is very high. And actually, we can see for the sweep, there will be some confusion between sweep and slide. And we can see this is because that for the slide motion and the sweep motion, it has some similarity, right? For these two different motions, but we can still identify there's only an error rate with 2.73. Next, if we train the model on S1, but we test on S2, and the accuracy is still very high, but not that high. Although it is still 95.5, but we can see the diagonal dominance is affected. So this shows the training ability for the cross domain, from training and test. Also, we also perform to train on S1 but test on S3. We still achieve accuracy of 93, but here that the slide there will be a bit high error probability compared to the roll motion. So which means that even we train our model in S1 in the office scenario, it's a very complex multipath scenario, but it can be used in some other scenarios. And actually, in our paper, we have shown that. So the delayed Doppler domain channel will be better for this kind of cross-domain transition. So we can train in S1, and it is still effective in S2 and S3. Okay, so what matters is the orientation. We can see if we change the orientation station, for example, to 30 degrees, and the accuracy is reduced to around 18.2. And if we further increase the orientation degree to 60 degrees, so the the accuracy is only 17.2%. So which means that what matters for our system, that is the Doppler projections will shrink and the patterns will deform because of this kind of orientation change. And this will be very several for this circle and the clap. So if we change orientation, perhaps we can not clearly identify the motions of the circle and the clap. Okay, and that's all. And thanks a lot for your listening. Okay, thank you.
Okay, thanks, Professor Yuan, for your very wonderful and very informative talk. So we do have received some questions from the audiences. And so the first question from the audience is that you mentioned that this method uh, characterize the physical characteristics of the signal in the delay-Doppler domain. Could you elaborate on what these specific physical characteristics of the DD domain are?
Okay, so yeah, let me move the slide. Okay, so actually, I believe that the physical characteristics actually comes from here. So if we have scatters in the scenario, then it will maybe result in a delay shift. So based on this delay shift and this kind of a line of sight path, we know that where might the scattering spin, right? Because if we have a transmitter, if we have a receiver, then we can illustrate eclipse. So we can make sure that the scatter will be located on the eclipse, right? So that is the first one. And for the second part, if we have the Doppler information, we can very easily obtain the speed of the moving target. So I believe these are what I mean. So we can extract the physical characteristics from the delayed Doppler domain channel.
Okay, thanks for your answer. And the second question is, how specifically does the DD domain-based ISAC approach improve the system's adaptability to different scenarios? For example, a high mobility scenario versus a dense multipath scenario.
Yeah, I believe so. Yeah, as we discussed here, so for the high mobility targets, the quasi periodicity is very useful because that even the target has a very high speed, it can be transformed to the fundamental rectangle. Even there's some ambiguities, but we can still have an estimation result of this target by using this periodicity in Doppler. For the multipath scenario, I don't think there are some significant benefits by using this DD waveform. Yeah.
Okay, thank you very much. So I also have some questions.
Yeah.
So first of all, maybe you are aware of that recently the 3GPP has reached agreement that the 6G will continue using CPU
Yeah.
FDM and
Yeah.
DFU FDM.
Yeah.
So as long as I can recall that OTFS originally has been proposed as a candidate 6G waveform. So can you comment on this? So will OTFS or in a more general sense, DD domain waveform, plays a role in the future next generation wireless communication system?
Yeah, actually, for this part, I'm not that optimistic because that so for the communication system, it is a very huge the standardization organization. So the different parties have to consider their benefits, and if they have already get some issued patents on relevant topics, right? So I believe that because for some major players in this area in communication standardization, so they have already got many standards on OFDM, and also as in our previous paper, we have proved that the OFDM can achieve the best sensing performance in some maybe uh, for the target with not that high moving speed, right? So I believe that actually for 60 or for the next 10 years, we should still focus on FDM for both communication and sensing. But sometimes maybe for some other use cases, for some specific use case, such as the military or for some satellites, perhaps we can use this kind of new delay-Doppler waveform to solve some corner cases. But for general cases, we should stick to OFDM. And that's my point.
Okay, thank you. Very good point. So another question is that I noticed that you always use delayed Doppler domain waveform design. So can we see that this kind of delayed Doppler domain waveform is a generalization of OTFS, or can we see OTFS is just one of this kind of waveform designs? Do we have other types of DD domain waveform designs?
I think that's a good question. So I believe that some of you may have read some papers on some other kind of delay-Doppler waveforms such as ODDM and also the DDMC. And also there's another waveform that attracts maybe much attention recently, the AFDM. So as for the delayed Doppler waveform, we focus on the delayed Doppler domain, but for the AFDM, perhaps they focus on the a kind of a fine domain. But I think for these new developed waveforms, they always focus on how to convert this kind of time frequency channel to more stable and more sparse channel in other domains. So by using some mathematic the manipulations. So indeed, I think OTFS perhaps it can be seen as one of the delayed Doppler waveform. And also for delayed Doppler waveform, it is also only a subclass of the general new waveform. So we show a logo here. So for this new waveform, what we want to achieve, perhaps it should be compatible with OFDM, and it should provide the benefits of OTFS, ODDM, and FDM. That is to provide better communication performance, perhaps in the high mobility scenario. And also it should be good for sensing. So it should provide some benefits for sensing as well. So yeah, I think so. The delayed Doppler waveform is not all. There are so many new waveforms developed recently.
Okay,
Different
thanks.
domains. Yeah.
Thanks, Professor Yuan, again for the wonderful talk and for your answers. I guess that's all for today's lecture, and thank you again. So
Thank you.
before I let you go, I just wish to advertise that next week we will have the same time we will have Professor Andrew Zhang from University Technology Sydney to present his talk on bistatic sensing. Okay. Thank you all. I think that's the end of the talk. See you. Bye bye.
Thank you. Yeah, see you next week. Bye.
好的，感谢两位老师，下周再见。
我